You've probably heard that the universe had a beginning. The Big Bang, around 13.8 billion years ago. A moment when everything suddenly existed. What's strange is how comfortable we are with that idea now. A cosmic start button. But here's what we don't sit with as often. If it had a beginning, does it have an end? And if it does, what does that actually look like? Not in a vague, someday far away sense, but mechanically, physically. What are the actual processes that could bring everything, every galaxy, every star, every atom, to some kind of final state? Turns out, physicists have calculated 3 main possibilities, and each one reveals something different about the fundamental architecture of reality. These aren't guesses. They're logical conclusions based on what we know about gravity, expansion, and the mysterious force pushing the cosmos apart. And depending on which one is correct, the universe could end in ice, in darkness, or in fire. Let's think about this carefully. The first thing to understand is that the universe is already doing something. Right now, it's expanding. Space itself is stretching, carrying galaxies away from each other. This isn't new information. Edwin Hubble figured this out in 1929. But what matters here is the rate. How fast is this expansion happening? And more importantly, is it changing? For decades, scientists assumed the expansion was slowing down. Gravity, after all, pulls everything together. It seemed logical that the mutual gravitational attraction of all matter in the universe would gradually break cosmic expansion. Eventually, maybe, it would stop altogether. Except that's not what's happening. In 1998, 2 independent teams of astrophysicists made measurements that didn't make sense. They were studying distant supernovae, exploding stars that serve as cosmic distance markers, and discovered that the expansion of the universe isn't slowing down. It's accelerating, speeding up. Something is actively pushing space-time apart. And whatever that something is, it's stronger than gravity on cosmic scales. They called it dark energy because honestly, we don't know what it is. We just know it's there, and it makes up about 68% of all energy in the universe. This discovery won the Nobel Prize, and it completely changed our understanding of cosmic fate. Because if expansion is accelerating, the universe probably isn't going to collapse. Which brings us to the first scenario, the Big Freeze, sometimes called heat death, though that's a bit misleading. This is what happens if dark energy continues doing exactly what it's doing now, pushing everything apart forever. Here's how it unfolds. Over the next few trillion years, galaxies continue receding from each other. The accelerating expansion means that eventually, every galaxy outside our local gravitational neighborhood disappears beyond the cosmological horizon. The night sky goes dark. Within our own galaxy, or rather within Milkdromeda, the merged product of the Milky Way and Andromeda, star formation gradually slows. Gas clouds run out. The last stars are born around 100 trillion years from now. Small, dim red dwarfs that burn for tens of trillions of years more. But even they eventually die. Around 10 to the 14th years from now, that's 100 trillion. The last star burns out. The universe enters what's called the degenerate era. No more starlight, just the fading remnants. White dwarfs, neutron stars, black holes, and free-floating planets drifting in the dark. These remnants persist for an almost incomprehensible time. White dwarfs cool, black dwarfs form, completely cold, dark stellar corpses. Over scales of 10 to the 32nd power years, even protons begin to decay. Matter itself slowly disintegrates. By 10 to the 40th years, black holes, the most enduring structures in the cosmos, evaporate through Hawking radiation. The supermassive black hole at the center of our galaxy, which is 4 million times the mass of the Sun, takes 10 to the 100th power years to disappear. And then there's nothing, just photons, particles of light spreading through ever-expanding space, growing colder and more diffuse. The universe approaches a state of maximum entropy, perfect equilibrium, no energy gradients, no possibility of work or change. Not frozen in the sense of cold and solid, but frozen in the sense of thermodynamically dead. This is the heat death, a universe that has run out of usable energy. It doesn't explode, it doesn't collapse, it just fades, expands into eternal silence. This is currently the scenario most cosmologists consider most likely, based on measurements of dark energy's behavior. But it's not the only possibility. If you'd like to explore more of these cosmic questions, what happens at the edges of existence, what we can know, and what remains fundamentally mysterious, consider subscribing. We examine the biggest scales and smallest puzzles every week. The second scenario is stranger and more violent. The Big Rip. This happens if dark energy isn't constant, but increasing. If the force pushing the universe apart gets stronger over time. Scientists call this phantom energy. And here's what makes it terrifying from a physics perspective. It doesn't just accelerate expansion. It eventually overpowers every other force in nature: gravity, electromagnetism, the nuclear forces holding atoms together. Here's the timeline. Initially, it looks like the Big Freeze. Galaxies recede, the sky goes dark. But then around 20 billion years from now, much sooner than heat death, dark energy's intensity crosses a threshold. It begins tearing apart gravitationally bound structures. First, galaxy clusters dissolve. Then individual galaxies break apart. Stars scatter. Around 60 million years before the end, solar systems come unbound. Planets drift away from their stars. 3 months before the final moment, planets themselves disintegrate, torn apart by the expanding space between their atoms. In the last moments, molecules break, atoms shred. Even atomic nuclei split apart as space expands faster than the nuclear strong force can hold them together. The universe ends not in silence, but in total annihilation. Every structure, every pattern, every bit of organization ripped to fundamental particles and then beyond. Current observations suggest this isn't happening. Measurements of dark energy show it behaving as a cosmological constant, not strengthening, but we can't rule it out completely. The uncertainty in our measurements leaves room for phantom energy. If dark energy's equation of state is slightly different than we think, the rip is possible, which, when you consider it, means we're measuring the universe's fate with extraordinary precision, but still can't be completely certain. The third scenario goes the opposite direction entirely: the Big Crunch. This is what happens if dark energy isn't permanent, if it weakens or reverses, if gravity wins. The expansion of the universe slows, stops, and reverses. Space itself begins contracting. Galaxies that were receding start approaching. The cosmic microwave background radiation, currently at 3 Kelvin, just barely above absolute zero, begins warming. The universe heats up. As space contracts, everything gets closer, denser, hotter. Over billions of years, galaxy collisions become common, stars pack together. Eventually, the night sky blazes with starlight from every direction as galaxies merge into a single superstructure. The temperature rises, stars evaporate, matter breaks down into plasma. The universe compresses into conditions similar to the early moments after the Big Bang, but in reverse. Hotter and hotter, denser and denser, until perhaps everything collapses into a singularity. All of space-time crushed into a point of infinite density and temperature. Some versions of this scenario suggest the crunch could trigger another Big Bang, a cyclical cosmos, expanding and contracting eternally. Others suggest it simply ends in that final singularity. Based on current measurements, the Big Crunch seems unlikely. The universe's expansion is accelerating, not slowing. For a crunch to occur, dark energy would need to somehow reverse, a mechanism we have no evidence for. But the universe has surprised us before. So here we are. 3 possibilities, each grounded in real physics. The Big Freeze, where expansion continues until everything grows cold and dark over trillions upon trillions of years. The Big Rip, where accelerating dark energy tears apart every structure in a cosmic unraveling. The Big Crunch, where gravity eventually wins and everything collapses back into itself. What's remarkable isn't just that we can calculate these scenarios. It's that we can measure which one is most likely. Astrophysicists study the expansion rate, the density of matter, the behavior of dark energy, and from those measurements, predict the fate of everything. Current data points toward the Big Freeze, a long, slow cooling, an asymptotic approach to silence. But the margins of error are still wide enough that we can't completely rule out the alternatives. And there's something profound in that uncertainty. We live at a moment in cosmic history where we can observe enough of the universe to ask these questions meaningfully, but not enough to answer them with absolute certainty. Drop a comment and tell me which scenario feels most strange to you: the eternal fade, the violent rip, or the cosmic collapse. What matters, I think, is less about which specific ending awaits and more about what it means that endings exist at all. The universe isn't static. It isn't permanent in the way we intuitively imagine. It's a process with a beginning we can trace and an end we can calculate. That temporality, that finitude, doesn't diminish the cosmos. If anything, it makes this moment more remarkable. We exist in the middle chapters of a story that has a beginning and will have an end, able to read backward toward our origins and forward toward our conclusion. That's not a small thing. The stars will eventually go out, yes, or the fabric of space will tear, or everything will collapse. But for now, for this brief window in deep time, the universe is full of light and structure and complexity. Galaxies spiral, stars fuse hydrogen, atoms arrange themselves into patterns capable of understanding their own existence. We're here to witness it, to measure it, to contemplate what it means. That might be the most interesting part of all.